Hi friends, welcome to our YouTube channel RJ Academy. The main aim of this lecture series is to provide the detailed solutions of the Telangana State ECET question paper of 2020, detailed solutions of the electrical engineering in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes to mobile. If any improvements are needed in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the first question. See the question here. A battery of EMF 4 volt has an internal resistance of 0.2 ohm. Where a load resistance of 1.8 ohms is connected across it, the potential difference across its terminal will be. So basically they are given a battery of voltage 4 volt and also internal resistance of 0.2. Suppose if they are going to connect a load of having the resistance of 1.2 ohm, then what is the voltage across the terminals of the battery, or simply we have to find what is the voltage across the load of 1.8 ohms we need to figure out. So the four options, option B 3.6 volt is the correct solution of this question. So let's solve this numerical. So in this question basically they are given a battery of voltage 4 volt and an internal resistance of 0.2 ohm, means or simply we can call it as a source resistance. So they are going to connect a load across this battery, which is the load resistance of 1.8 ohm. So we have to find what is the voltage across these terminals of the battery, or simply the load voltage we need to figure out. So this is what we need to figure out in this question. So this is called as basically a series. So these two are in series. So therefore by applying the voltage division principle, which is the voltage across the load is equal to supply voltage into the load voltage, the load resistor by sum of the resistors which are present in the circuit, which is Vs into RL by Rs plus RL. So Vs is equal to 4 volt and RL is equal to 1.8 ohm and Rs is equal to 0.2 and RL is equal to 1.8. You can substitute here. We are going to get 0.2 plus 1.8 is 2. So therefore 2 ones are 2 2s are. So 1.8 into 2 is nothing but 3.6 volt. So therefore the load voltage is equal to 3.6 volt. So by applying the voltage division principle, we have figured out the voltage across the load resistor RL is equal to 3.6 volt is the correct solution of this question, which is 3.6 volt. Now we are going to solve the second question. See the question here. An iron ring of 10 cm in diameter and 8 cm square in cross-sectional area is wound with 300 turns of wire. For a flux density of 1.2 Weber per meter square and a relative permeability of 500, what is the inductance of the coil we need to figure out. So basically there is a iron ring. On that iron ring we are going to wound the coil of number of turns is 300, and also they are given the diameter of this iron ring they already given, which is called as a 10 centimeter, and the cross-sectional area of this iron ring is also they are given 8 centimeter square, and the flux density which is present in the iron ring is 1.2 Tesla. So based on this, and also they are given the relative permeability of this iron ring is 500. So based on this we have to find what is the inductance of this coil we need to figure out. So the four options, option B 0.1440 Henry is the correct solution of this question. So let's solve this numerical. So basically in this question they are given an iron ring. So this is the iron ring. On this iron ring they are going to wound the coil, and the number of turns of this coil they are given, which is 300 turns. So now based on this, suppose if I am going to pass some amount of current I, so because of this current I, whenever a current is passing in a wire, it is going to produce the magnetic field. So this iron ring is going to have certain amount of magnetic field. That magnetic field intensity also they have given, which is 1.2 Weber per meter square, and also they are given the overall diameter of this ring. So this overall diameter of the ring also they have given, which is equal to 10 centimeter. If you want to convert in terms of meters, which is 10 into 10 to the power of minus 2 meters, and also they are given the area of this core. So this is called as the area of this core. The area of this iron ring is also they are given, which is 8 centimeter square. If you want to convert in terms of meters, which is 8 into 10 to the power of minus 4 meter square, and also they are given the relative permeability of this iron core also they have given, which is 500. It is not having any unit, it is a unitless. So based on this we have to find what is the amount of inductance of this coil we need to figure out. So here these are the data they have given, which is the relative permeability of this iron core, which is 500, and the number of turns which are going to wound on this iron ring, which is 300 turns. and the area of this iron core they have given, which is 80 centimeter square. 8 centimeter square, if you want to convert in terms of meters, which is 80 to 10 to the power of minus 4 meters square, and the diameter of this iron ring they have given, which is equal to 10 centimeter. If you want to convert in terms of meters, which is 10 into 10 to the power of minus 2 meters. And also they are given the magnetic flux density which is flowing in this iron ring, also they are given, which is 1.2 Weber per meter square. So based on this data we have to find what is the value of the inductance of this coil we need to figure out. So basically, what is the amount of magnetic field intensity? The magnetic field intensity is equal to mu into small n into I, where small n is called as the, mu is called as the permeability, whereas small n is called as the number of turns per unit length. The number of turns per unit length we need to consider. So small n is called as the number of turns per unit length, and I is called as the current which is passing in this coil. So the small n is called as the number of turns per unit length. Suppose if the total length is L, suppose if this total length is L, so if the total length is L, then the number of turns are present is N. So N turns are present in a L length, so N turns are present in a length of L. But if I want to find the number of turns present in unit length, means I want a divide by L, so therefore N by L. So these are the number of turns which are present per unit length. So for a length of L, the turns present are capital N, but I want to find the number of turns present for unit length, means divide by L on both sides, we are going to get capital N by L is called as a small n, which is called as the number of turns per unit length. So therefore simply small n is equal to total number of turns present per total length, which is capital N by L. So what is this total length? The total length of this circumference is nothing but this is basically circumference of a circle. Circumference of a circle is equal to 2 pi r. So circumference of a circle is equal to 2 pi r, but 2 into r is called as the diameter. So therefore pi into d is called as the, because 2 into r is called as the diameter. So therefore pi length, this circumference is equal to pi into d. So therefore this L is equal to 2 pi r, but 2 into r is called as a d. So therefore pi into d, and remaining everything is same. But mu is equal to mu naught mu r into Ni by pi d. So this is the overall expression of the magnetic field present in this iron ring. So now the flux. So because of one turn, how much amount of flux which is produced, which is equal to, the flux is equal to product of the magnetic flux density into area of the iron core. But if I want to find the overall flux linkage, in this iron core is nothing but due to n number of turns. So if pi is the flux per only one turn, because there are n turns, so to overall flux linkage is equal to total number of turns into flux per one turn. So therefore the overall flux linkage is equal to total number of turns into flux per one turn, which is n into phi. But phi is equal to b into a, so substitute b into a, but b value we already know, which is this expression. So substitute here, we are going to get in this format. So now if you simplify this one, we are going to get, which is n into n is n square. So n square a into mu naught mu r I by pi d. So this is the expression of the overall flux linkage, but we have to find what is the value of the inductance. Inductance is the ratio of the overall flux linkage by current passing, which is L is the ratio of the overall flux linkage by the amount of current passes. So therefore lambda by I is nothing but we are going to get n square into a into mu naught mu r by pi into d. So you know each and every value, just substitute here and do the simplification, we are going to get the result. So mu naught is equal to 4.10 to the power of minus 7 and mu r is equal to 500 and n is equal to 300. So do the square, and area of the iron core is equal to 8 into 10 to the power of minus 4, and pi into d value they have given already, it is 10 centimeter, means 10 into 2 10 to the power of minus 2 meters. So therefore if you solve this expression, if you solve all these things, we are going to get finally the inductance of this iron, the inductance of this coil which is wound on this iron core is nothing but 0.144 Henry. So this is the correct solution of this question. Suppose in the same question, if they ask what is the value of the amount of current passing in this coil, if they ask you, then we can easily figure out from this expression, which is, I have already told you, B is equal to mu naught mu r into Ni by pi d. But I want to know what is the value of the current I. So current I is equal to, just do the cross multiplication, we are going to get B into pi d by mu naught mu r into N. So B value we know, which is 1.2, pi into D value we know, which is 10 centimeter, means 10 into 10 to the power of minus 2, and mu naught is 4.10 to the power of minus 7, and mu r is equal to 500 and n is equal to 300. So if you solve this one, we are going to get 2 amperes. Suppose if they ask the amount of current passing in this coil, means the answer will be 2 amperes. But in this question they have not asked, but still in the future examinations they may ask the amount of the current I, so I have did this one. So therefore from this data we can figure out the value of the current I is equal to 2 ampere and the inductance of this coil is equal to 0.1144 Henry is the correct solution of this question. So now we are going to solve the third question. See the question here. The self-inductance of two coils are L1 is equal to 2 Henry and L2 is equal to 8 Henry. The coil L1 produces a magnetic flux of 80 microweber, of which only 60 microweber are linked with coil L2. The mutual inductance of the two coils is, so basically they are given two coils L1 and L2, and the L1 and L2 also inductance they are given, which is L1 is equal to 2 Henry and L2 is equal to 8 Henry. And also they are given that if you pass the current in the inductor L1, it is going to produce a flux of, they are given 80 microweber, out of which only 60 microweber is going to link with the secondary coil L2. So based on this we have to find what is the mutual inductance of these two coils we need to figure out. So these four options. Option C, 3 Henry is the correct solution of this question. So let's solve this numerical. So basically in this question they are given two coils L1 and L2. The coil 1 has an inductance of 2 Henry and the coil 2 has an inductance of 8 Henry. So now suppose there is a current of I1 flowing in the coil 1. So because of this current I1, it is going to produce some amount of flux. So in this question they are given the total flux produced by this coil 1 is they are given, which is equal to 80 microweber. This is the total flux which is produced by the coil 1. So out of this only 60 microweber is going to link with the L2. So therefore you can see only 60 microweber is going to link with the coil 2 and the remaining 20 is not going to link with the secondary coil, or simply we can say that the remaining 20 microweber is going to link only with the coil L1 itself. So therefore we can say that only the mutual flux or the useful flux is the flux which is linking both the coil 1 and the coil 2. So the coupling coefficient is nothing but the coefficient of coupling is the ratio of the useful flux by the total flux. The useful flux means the flux which is linking between the two coils is called as the useful flux, whereas the total flux is called as the flux which is produced by this coil 1, which is in this question they have already given the useful flux or the flux linking with both the coils is 60 microweber and the total flux which is generated is 80 microweber. So therefore 0 cancels, microweber cancels, which is 6 by 8 is nothing but 3 by 4. So the value of K, which is 3 by 4, where K is called as the coefficient of coupling. So the value of K can range from 0 to 1. 0 means we can say that the useful flux is 0, means not even the flux produced by coil 1 is not at all linking with the coil 2, or we can say they are totally isolated coils. So therefore there is no flux linkage. Then the K value is equal to 0. If K is equal to 1 means they are tightly coupled, means whatever the flux generated by this coil 1 is totally linking with the coil 2, there is no leakage flux, then we can say they are tightly coupled. So K can range from 0 to 1. So therefore K is the ratio of useful flux between the mutual flux between the coil 1 and coil 2 by the overall flux produced by the coil 1. It is called as the K. It is the ratio of useful flux by total flux. So now K is equal to M by under root over L1 L2. So if you take this one, M is equal to K into under root over L1 L2. So K value we know, which is 3 by 4 into L1 is 2 Henry and L2 is 8 Henry. So therefore 8 to the 16. So root over 16 is 4. So 3 by 4 into 4 is nothing but 4 cancels. So we are going to get M is equal to 3 Henry. So therefore the mutual inductance between the coil 1 and the coil 2, which is 3 Henry. So 3 Henry is the correct solution of this question. So therefore the only thing that you need to remember is the coefficient of coupling is the ratio between the useful flux or the mutual flux between the coil 1 and coil 2 by total flux produced by the coil 1. So now we are going to solve the fourth question. See the question here. For the series RLC circuit shown below, the supply voltages. So basically they are given a series RLC circuit and we have to find what is the supply voltage we need to figure out. The voltage across the resistor is 100 volt and the voltage across the inductor is 200 volt and the voltage across the capacitor is 200 volt. So based on this condition of voltage across the three elements, we have to find what is the supply voltage or the RMS value of the supply voltage we need to figure out. So out of the four options, option C, 100 volt is the correct solution of this question. So let's solve this numerical. So in this question, they are given basically a series RLC circuit. So in the series RLC circuit, the voltage across the resistor is 100 volt and the voltage across the inductor is 200 volt and the voltage across the capacitor is 200 volt. So we have to find what is the supply voltage at this connection. We need to figure out. As you can see clearly, it is series RLC circuit. So I am going to take the current as a reference vector. So current as a reference vector. So in a series RLC circuit, for resistor, the voltage across the resistor and the current are going to lie in the same phase. So VR and I are in the same phase. Whereas in the inductor, the current is going to lag the voltage of the inductor by 90 degree. So current is going to lag the voltage across the inductor by 90 degree. Similarly in a capacitor, the voltage, or we can say the current is going to lead the capacitor voltage by 90 degree. So current is going to lead the capacitor voltage by 90 degree. So now you can see clearly what is the overall supply voltage is the vector quantity, which is the voltage across the resistor plus voltage across the inductor plus voltage across the capacitor. These are the vector quantities. Because it is a AC analysis means we have to go for the vector addition. If it is DC analysis means so for AC analysis we go for the vector addition. For the DC analysis we go for the arithmetic addition. So therefore as it is the AC analysis we go for the vector addition. So VR is nothing but it is in same phase. So therefore 100 at an angle of 0 degree plus VL, it is going to lead the I by 90 degree. So therefore this voltage magnitude they have given 200. So 200 at an angle of plus 90 degree. Whereas the capacitor voltage magnitude they are given 200, but it is going to lag by minus 90 degree. So therefore 200 at an angle of minus 90. So therefore 100 angle 0 is nothing but 100 and this 200 angle 90 means 200J and 200 at an angle of minus 90 means minus 200J. So plus 200J and minus 200J cancels. So finally we are going to get the supply voltage is equal to 100 volt, or simply we can say this is called as a resonance condition. At resonance condition, the circuit is purely resistive. So therefore, the inductor voltage and capacitor voltage have the same magnitude, but they are in opposite in direction or a phase of 180. So overall value will get cancels. So therefore, the total supply voltage is going to drop across the resistor at the resonance condition. So therefore, the supply voltage is equal to voltage across the resistor, which is equal to 100 volt. So now we are going to solve the fifth question. See the question here. The moving iron instruments of dash scale. So what is the nature of the moving iron instruments? The scale. So therefore, out of the four options B, non-uniform is the correct solution of this question. So moving iron instruments have a non-uniform scale. So now we'll discuss something more about this one. So now we'll discuss the different types of measuring instruments which are used in the measurements, which are the PMMC, MI and EMMC. So PMMC is called as a permanent magnet moving coil. So in this there will be a moving coil with a permanent magnet. So this measuring instrument is used to measure only the current and the voltage. So for current and voltage it is going to have the linear scale. So for current means we are going to measure with the help of ammeter, and the voltage means we are going to measure with the help of voltmeter. So this both will have the same scale. The nature is linear scale. So therefore here in this PMMC, the deflection torque is directly proportional to current. So therefore, whenever the current is positive, TD is positive, and whenever the current is negative, TD is also negative. So therefore, for AC, if you give AC supply, the average value of the deflection torque is equal to 0. So therefore, the pointer will never view if you give the AC. So therefore, it is used only for the DC, but not for the AC. Similarly, moving iron instruments. For moving iron instruments, there will be a stationary coil. The coil is very stationary to produce a magnetic field, but there will be a moving iron. A soft iron piece will be there. It can be used either by repulsion property or the attraction property by which the moving iron can repel or attract. So they are going to use a moving iron or soft iron piece. So here it is used to measure both the current and also the voltage, and here they have the non-linear scale because the deflection torque is directly proportional to square of the current. So therefore simply we can say that as it is directly proportional to square of the current, when the current is positive, TD is also positive, but when the current is negative, negative square is again positive. So again TD is positive. So if you give AC or DC supply, the average value of the deflection torque is always positive. So therefore the pointer will move for both the AC and also DC supply. So therefore MI instrument is used for both AC and DC supply. Whereas EMMC, electromagnetic moving coil, this device can measure the current, voltage and also power. But for current it will have the nonlinear scale, and for voltage it has the nonlinear scale, but for the power it has the linear scale. So basically the average power, here power means it is going to measure the average value of the power. It is going to measure the average value of the power, and the deflection torque is directly proportional to square of the current. So if you give AC or DC supply, if you give AC supply for a positive value current, TD is a positive. For negative value of the current also, negative square is again positive. So therefore, if you give AC or DC, the still the diffusion torque is always positive, or average value is always not equal to 0. So it works for both AC and DC supply. So these are some of the important properties of this one. See, in the PMMC and MI, see in the PMMC and MI and EMMC, we are going to use the spring as a control torque. So therefore, spring is used. So therefore, TC is directly proportional to theta. Here also TC is directly proportional to theta. Here also TC is directly proportional to theta. At a steady state, TD is equal to TC. So therefore, theta is directly proportional to I. So whenever the theta is directly proportional to I, it is called as a linear scale. Whereas here TC, so theta is directly proportional to I square, so it has non-linear scale. Whereas here theta is directly proportional to I square, so it is as the, so here linear scale for current and linear scale for voltage. So non-linear scale for current and non-linear scale for the voltage, and in this case theta is directly proportional to I square, so I is equal to V by R. So if you substitute here, we are going to get V square by R. So therefore, it has the non-linear scale for both current and voltage, but theta is directly proportional to average power you are going to get. So we can say that for PMMC, it has the linear scale for current and also linear scale for voltage, because I is equal to V by R. So therefore, it has linear scale for current and voltage, and here in the MI, it has the non-linear scale for current and also non-linear scale for voltage also. Similarly, it has the non-linear scale for current, non-linear scale for voltage, and it has the linear scale for the power. Always the wattmeter or the EMMC is going to measure the average value of the power. So linear scale means simply we can say that you can see between any two divisions the gap is same for each and everywhere. So throughout this scale you can see the gap between each and every division is same. So it is uniform over the total scale. It is called as a linear scale. Otherwise, if you see clearly at the near point the divisions are very close to each other, whereas as you move further and further you can see the divisions are very far away. So therefore we can say it is cramped. It is cramped at the nearer and it is overspread over the far end. So overspread. So we can say the divisions are not uniformly spread over the total scale. So it is called as a non-linear scale. Initially they are crowded and later they are widespread. So therefore it is called as a non-linear scale. So now we are going to solve the sixth question. See the question here. A 6-pole wave-wound DC shunt generator has 300 connectors on its armature. The flux per pole is 20 milliweber and when it runs at 1000 rpm, the EMF generated is. So basically they are given a DC shunt generator. It is going to have a 6 poles, and here the armature, the connectors are wounded in a wave wound, and it is going to have armature connectors of 300, and also the flux per pole is 20 milliweber. So and it is going to run at 1000 rpm. So based on this we have to find what is the EMF which is generated. So what are the four options? Option C, 300 volt is the correct solution of this question. So let's solve this numerical. So in the question they are given the number of poles is equal to 6. And also they are given that the armature connectors are wounded in the wave wound. So wave wound means the number of parallel paths is equal to 2. Suppose if in the case they give the lap winding, so if the armature connectors are connected in the lap winding means the number of parallel paths is equal to number of poles. So the easy way to remember is in lap winding there is a P, so therefore here is equal to P. Here wave you can see there are 2 dots. So we can say 2 dots means 2. So therefore number of parallel paths is equal to 2. So this is the easy way to remember the number of parallel paths for the wave winding and the lap winding. But in the question they are given it is a wave winding. So number of parallel paths is equal to 2. And also they are given the total number of armature connectors is equal to 300 and the flux per pole. So therefore one pole is going to produce a flux of which is 20 milliweber. And also we are going to rotate the shaft at a speed of 1000 rpm. Then how much amount of EMF which is going to get generated in this DC shunt we need to figure out. So we are going to rotate this shaft with a speed of 1000 rpm. So based on this we have to find what is the amount of EMF which is generated by this DC shunt generator we need to figure out. So basically the formula is here P5 into N by 60 into Z by A. So this is a very basic formula where P the number of poles is equal to 6 and the flux per pole which is 20 milliweber means 20 into 10 to the power of minus 3 and the speed they have already given which is 1000 rpm by 60 into the number of armature connectors is equal to 300 and the number of parallel paths is equal to 2. So therefore I have substituted all these things, and if you do the simplification finally we are going to get the amount of EMF generated at all these conditions is equal to 300 volt by this DC shunt generator. So 300 volt is the correct solution of this question. So now we are going to solve the seventh question. See the question here. A generating station is to supply 4 loads whose peak loads are the 12 megawatt, 7 megawatt, 11 megawatt and the 15 megawatt. The diversity factor of the power station is 1.5. Then what is the maximum demand on this station we need to figure out. So here out of the 4 options, option B 30 megawatt is the correct solution of this question. So basically there are 4 loads which are having the peak demand also they have given for each and every load. So and also the maximum demand on the power station also they have given. Then based on this, see that we need to figure out, and also they are given the diversity factor of the power station they are given. So now we have to find what is the maximum amount of load demand on the power station we need to figure out. So out of the 4 options, option B 30 megawatt is the correct solution of this question. So let's solve this numerical. Suppose there is a power generating station, and here suppose it is going to send the power to the 4 loads. Suppose let me take, there are 4 houses, house A, house B, house C and house D. So basically these are the loads. So for the house A is going to have a maximum demand of 12 megawatt, and house B is going to have a maximum demand of 7 megawatt, and house C is going to have a maximum demand of 11 megawatt, and house D is going to have a maximum demand of 15 megawatt. Suppose if all these things are connected to the power station and is going to have the power station is going to have diversity factor of 1. Diversity factor of the power station is equal to 1.5. So based on this we have to find what is the maximum demand on the power station we need to figure out. So basically the diversity factor is the ratio of the sum of individual maximum demand of the loads, the sum of individual maximum demand of the loads by the maximum demand on the power station. So we can say clearly, see each house is going to have different types of light bulbs, fans, so different types of loads are going to present for each and every house. So therefore, if all these things are connected, so the maximum demand on the power station we need to figure out. So it is a ratio of the sum of individual maximum demand of loads by the maximum demand on the power station. So now the diversity factor is equal to 1.5 is equal to, then what is the summation of individual maximum demand of the loads, which is we have to add all these loads maximum demands, which is 12 plus 7 plus 11 plus 15. So therefore 12 plus 7 plus 11 plus 15. So we have this equation with only one unknown. So therefore 1.5 is equal to 12 plus 7 plus 11 plus 15 is equal to 45. So 45 by maximum demand on the power station. So if you take this one here and if you do the division, so finally we are going to get the maximum demand on the power station is equal to 30 megawatt. So therefore 30 megawatt is the maximum demand on the power station. See, you may have small doubt. Then if you see clearly, if you add all these things, the sum of individual maximum load is nothing but which is you got 45 megawatt. So if you add all these loads, the peak value of the loads of each and every house, you are going to get the 45 megawatt. But if you see clearly, the maximum demand on the power station is only 30 megawatt. Then where is the 15 megawatt means? See, if you add all the maximum demand of the loads which is 45 megawatt, but from this equation you got the maximum demand on the power station is only 30 megawatt. It indicates that, see, it is not possible all these houses are going to on at the same time. If suppose house A is on, switched on, but the house B is going to get switch off, we don't know. So therefore at certain conditions we don't know that everyone is going to get turned on the loads at same time. So therefore some may be on and some may be off. So because of that we are going to get the 30 megawatt. So always the diversity factor is always greater than 1. The value of the diversity factor is always greater than 1. So these are the important points that you always have to remember. See, it is less than 45 because it is not possible that each and every, see, all the loads are going to turn on at the same time. So therefore because of that only we can say this is the 30 megawatt is the maximum demand which is going to receive because of all these loads on this power station at a condition of diversity factor is equal to 1.5. So now we are going to solve the 8th question. See the question here. The most efficient form of damping employed in electrical instrument is. So out of these 4 options we have to figure out the most efficient form of damping which is present in the electrical instruments we need to figure out. So out of the 4 options, option C eddy current damping is the correct solution of this question. So let's solve this one. So now we'll discuss something more about this damping. So basically why dampings are used in the electrical measuring instruments, because at steady state both the deflection torque and the torque both are equal. So therefore pointer will be at steady state at the rest. but due to some amount of oscillations are going to present at the steady state, or we can say the pointer is going to get oscillated at the steady state. So we have to reduce these oscillations as soon as possible. So therefore we are going to use the damping in such a way, so with the help of this damping it is going to absorb all the oscillations energy, so therefore it is going to reduce the oscillations in a very small amount of time. That is the purpose of using the damping in the measuring instruments. So basically there are the different types of dampings which are used in the electrical measuring instruments are three types, which are called as the air friction damping, fluid friction damping, and the eddy current damping. So whenever there are permanent magnets, we prefer to use the eddy current damping. So that is the reason eddy current damping is used in the PMMC, because there are the permanent magnet. So because of that only we are going to use the eddy current damping in the PMMC. Whereas the air friction damping is used in the EMI and also in the EMMC, we are going to use the air friction damping. So fluid friction damping is used for electrostatic voltmeter. There we are going to use the fluid friction damping. So now let me give you the best performance. So now we are going to compare these three damping systems based on the best performance. The performance of the eddy current damping is more higher when compared to fluid, and then it will be air friction. So 3 is greater than 2 is greater than 1 for the best performance. So the eddy current damping is having the best performance when compared to fluid friction damping, and then the air friction damping is going to get come. But if you want to see in the case of most preferred, the most preferred is always the eddy current damping, because in the fluid friction damping there is a possibility of the fluid is going to get leakage. So because of that we are not going to take it as the most preference. So therefore it will come in the last case. So then we are going to prefer the air friction damping, and then comes the fluid friction damping, because there may be a possibility of leakage of the fluid. So because of this nature only we are going to take it as the last case. But in the both these cases, in the best performance and the most preferred, always the eddy current damping is preferred. So therefore eddy current damping is the most preferred damping, and it is used only when there is a permanent magnets are there, then we are going to use this eddy current damping. And it is also used in the PMMC, and also we are going to use in case of the energy meters. In the energy meters also we are going to use this eddy current damping, energy meter. In these two instruments we are going to use the eddy current damping. So these are the some of the important facts or some of the important points regarding the dampings in the electrical measuring instruments. So now we are going to solve the 9th question. See the question here. A 100 volt DC series motor takes 45 ampere when running at 750 rpm. Its armature resistance is 0.22 ohms, while the series field resistance is 0.13 ohms. Iron and friction losses amounts to 750 watt. The shaft power of the DC series motor is. So basically they are given the armature resistance, field, or you can say the series field resistance, and also the supply voltage, and also the amount of current supplied by this DC motor also they have given. So based on this, and also they are given the iron and the friction losses. So based on this data we have to find how much amount of the shaft power, or the shaft is going to take how much amount of power we need to figure out. So out of the four options, option C, 3.041 kilowatt is the correct solution of this question. So let's solve this numerical. So in this question they are given a DC series motor, means the field winding is going to connect in series with the DC motor. So therefore the armature resistance they are given 0.22 ohm, and also the series field resistance is 0.13 ohm, and also they are given the supply voltage is equal to 100 volt, and the armature current drawn by this DC series motor is equal to 45 ampere. So now we have to find how much amount of the output power shaft, or the shaft power we need to figure out. How much amount of power received by the shaft we need to figure out. So if you draw the diagram, the power flow diagram of this DC series motor, the input power is called as electrical input power. The input power we are going to give the electrical power. So from this electrical power there is a copper losses because of resistance, series field resistance, and the armature resistance. So there is a copper losses because of this armature resistance and the series field winding. So there will be a small amount of copper loss. So therefore the electrical input power minus copper loss power is equal to the mechanical power. So the remaining power is going to develop as called as the mechanical power developed across this. So whatever the power which is subtraction of the electrical input power and the copper loss is called as the mechanical power developed. But because of some mechanical like iron and friction losses, a small amount of power is withdrawn. So therefore a small amount of power is lost because of these iron and friction losses. So the remaining power is nothing but shaft power. So therefore we can simply say that the losses in this machine are because of the copper loss and the iron and friction losses. But the input power is electrical power. So output power is equal to total input power minus losses. So therefore shaft power is equal to electrical input power minus losses. So shaft power is equal to electrical input power minus total losses. So we have to find what is electrical input power. Electrical input power is equal to supply voltage into supply current. So supply voltage is equal to 100 volt and the supply current is equal to IA, which is 45 ampere. So therefore 100 into 45, which is 4500 watt. So if you write in terms of kilowatt, which is 4.5 kilowatt. So electrical input power is equal to 4.5 kilowatt. So now the losses in the machine are because of the copper loss and the iron and friction losses. They've already given the question, which is iron and friction loss is equal to 750 watt. So we have to find the copper loss. So copper loss is equal to, these two resistors are connected in series. So overall resistance is equal to summation of individual one, which is RSC plus RA. So the power is equal to I square into net resistance, which is IA square into RSC plus RA. So copper loss is equal to IA square into RA plus RSC plus iron and friction loss is equal to 750. But IA is equal to 45. So 45 square into RA is equal to 0.22 and RSC is equal to 0.13 plus 750. So if you solve this equation, we are going to get 1458.75 watt. If you write in terms of kilowatt divided by 1000, we are going to get 1.458 kilowatt. So we know the total power loss in this DC series motor. Then we know the electrical input power also. So do the subtraction of electrical input power minus power loss. Electrical input power is 4.5 kilowatt and the losses in this DC series motor, which is 1.458 kilowatt. So if we do subtraction, we are going to get 3.041 kilowatt. So therefore the power received by the shaft is equal to 3.041, and this is called as the power flow diagram of this DC series motor. So now we are going to solve the last question of this lecture. See the question here. Three coils each having a resistance of 20 ohm and a inductive reactance of 15 ohm are connected in a star to a 400 volt 3-phase 50 Hz supply. Its power factor is. So basically we can say there are three coils. They are given the resistance and also reactance of these coils, and also these are connected in a star fashion, and they given the supply voltage, supply frequency also they are given. Supply voltage is the line voltage. So now based on this, we have to find what is the power factor of the load we need to figure out. So out of these four options, option D 0.8 lag is the correct solution of this question. So let's solve this numerical. So in this question they are given three coils. Three coils, they are going to connect in a star fashion. So we are going to give a supply of 400 volt 3-phase supply with 50 Hz frequency. So if they have not mentioned anything about this one, means it is by default it is a line voltage. Line voltage means across the two lines the voltage is called as the line voltage. So in this question, these are the coils. So they are given for particular this voltage and frequencies. The resistance is equal to 20 ohm and the reactance is equal to 15 ohm. So we can replace this coil by a RL circuit, or simply R and X. It is going to have some resistance and inductance, which is R and X. Similarly here also we can replace by resistor and inductor. Similarly here this coil I am going to replace by resistor and inductor, which is R and X. So now I am going to draw this diagram, which is impedance diagram. The base is always resistor and the height is called as the reactance and the overall hypotenuse is called as the mod of Z. So by using the Pythagoras theorem, the mod of Z is equal to under root over the two side square, or the square root of the side square, sum of side square, which is under root over R square plus X square. I want to find what is the power factor and the cos of means power factor. The cos is called as a power factor. It is the ratio of the adjacent by the hypotenuse, which is R by mod of Z. R by mod of Z is nothing but under root over R square plus X square. So you know each and every value. R is equal to 20 ohm and X is equal to 50 ohm. Substitute here, and if you solve, we are going to get 20 by under root over 20 square plus 15 square. So under root over 20 square plus 15 square is nothing but 25. So therefore 20 by 25 is nothing but 0.8. So therefore we can say the power factor is equal to 0.8 lagging, because always it's a coil. There is only resistor and inductor. There will be no capacitance. So definitely current is going to lag the supply voltage. So therefore we can say that it is a lagging nature. Lagging nature means always current is going to lag the supply voltage, and leading means current is going to lead the supply voltage. So we are going to take the reference as the voltage. So we are going to tell regarding the nature of the power factor based on the reference voltages we are going to take the reference as the voltage. Based on this, we are going to tell the power factor either lagging or leading. So whenever the current is going to lag the supply voltage, we call it as a lagging load, and whenever the current is leading the supply voltage, we call it as the leading load. But in this case, only a resistor and reactor is present, so therefore it is an inductive load. So current is going to lag the voltage, so therefore simply we can say it is a lagging agent. So 0.8 lagging is the correct solution of this question. So by this lecture, we have successfully completed some of the important questions of the Telangana State ECET question paper 2020 of W Electrical Engineering in a very detailed manner. And if you like the content of our channel, then please to like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever we upload a new video, the direct notifications comes on mobile. If any improvements are needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.